The most curious thing about the wing is its own specific shape that follows the basic principles of fluid mechanics. In this section, we are able to see the shape of the wing. We notice that the wing has a teardrop shape, and when the airplane starts moving in this direction, the airflow will hit the wing following these trajectories. But how does the wing rise when it is hit by the airflow? First of all, it is necessary to say that the wing is placed in a slightly inclined position to improve the airflow. In addition, the airflow entering at point A should have the same speed as the airflow at point B. In this situation, we are led to believe that the upper airflow is faster because it has to travel more airfoil surface than the lower airflow. Actually, speed has nothing to do with this situation. In fact, the upper airflow is simply more rarefied, which means that its molecules are more distant from each other while they travel across the wing surface. Lower airflow, on the other hand, is less rarefied, and therefore its molecules are closer to each other. The lower airflow.
So I would say that he's wrong in saying that velocity doesn't have anything to do with it. Really, what he's getting at there is the root cause of the Bernoulli's principle at a molecular level. Um, Macroscopic level, we just look at the overall result, right? It's higher speed, therefore lower pressure energy, um, therefore lift and so on, like the normal Bernoulli's principle discussion. But as I showed earlier in this lesson, the actual molecular interactions um, is why the pressure changes. The sort of the physical mechanism, let's call it, as to how the pressure changes. Um, so
The lower airflow has more molecules than the upper airflow. This creates a difference in pressure between the two parts. The low pressure on the top creates an upward suction effect that allows the wing and consequentially the whole aircraft to lift up. In addition, the numerous molecules of the lower airflow create a high pressure effect that allows the upward lifting of the wing.
So I'll add to that discussion about velocity actually being a factor and so on. Is that in this analysis? Yeah, he's got more air molecules in the bottom and so on. So that's obviously very good analysis. But what explains the restriction in a pipe? If you have a large diameter pipe restricts to a smaller diameter pipe, the pressure is measured as lower there. Still have the same number of air molecules, right? But they're forced to go faster. And so the previous analysis that I showed about the velocity effect and so on, and there being less time to rattle against the walls and so on, it all goes together. So none of it's wrong. It's just there's multiple factors, is what I would say.
This is not the only reason why planes fly. In addition to this pressure difference, the Coanda effect comes into play, which is the tendency of a fluid jet to stay attached to a nearby surface. This effect can clearly be shown by placing a simple spoon under running water. Or a common glass jar. The fluid, or in this case the airflow, moving along the wing surface causes friction, which tends to slow it down. This slowing only affects the molecules in direct contact with the wing. The airflow coming in a straight line hits the wing and follows its shape all the way out. This contributes to lifting the plane. So, the greater the airflow investing the wing, the greater the upward thrust. This is why planes, to take off, must
He was about to say the airplane has to go fast. I cut it off there briefly, but anyways, I wanted to show you this though. We can communicate the physics of it nice and clearly using Newton's laws. So you got the action force. Clearly, there must be an action force on the air to make it go down, since it's heading down. So that must have come from the wing, and then there must be a reaction force of the air on the wing, right? And that's what's specifically causing the lift force. So this goes right along with the other effect I showed, the Magnus effect. Basically, there's similar effects, and they have different names for different situations, right? So if you have a spinning ball, it drags the airstream and kicks it to one side, and that gives you the force for a curveball called the Magnus effect. In the case of air streamlines just hugging along a surface. They're just calling it this Coanda effect. Um, but really similar ideas all along.